Hey everyone, welcome back, and today let's solve Leetcode problem 3446 titled Sort Matrix by Diagonals. So we're given an n by n square matrix of integers grid, basically indicating that it has n rows and n columns, and we need to return the matrix such that the diagonals in the bottom left triangle, or portion of the matrix that includes the middle diagonal, very importantly, they are all sorted in non-increasing order. Quite frankly, I don't know why Leetcode states it or says it as non-decreasing order. They could just say decreasing order, but that's really what that means. And similarly, the diagonals in the top right triangle, or that portion of the rectangle or matrix, if you will, they would be sorted in increasing order, or in other words, the way Leetcode likes to phrase it, non-decreasing order. So in example 1, we have our input grid to be 173982 and 456. Those just indicate the values of our corresponding rows in the matrix, and we know that it is a 3 by 3 matrix, and in this case, we have an output of 823967451. And to better visualize how we get those values in those specific cells, as you can see here, initially your matrix is just really your matrix. We have 3 rows on the left triangle, which would be 4, 9, 5, 1, 8, 6, and 2 rows on the right part of the triangle, which would be 7, 2, 3. Notice how the middle is part of the left triangle, and all the diagonals on the left triangle of the matrix, they're actually then converted to be in decreasing order. 4 is in decreasing order, 9, 5 is in decreasing order, and 8, 6, 1 is in decreasing order. All of the diagonals, including again the middle one, that are in the bottom left triangle of the matrix. 7, 2 is in decreasing order, but since it is in the top right triangle of the matrix, we have to change it to be in increasing order. And 3 is just a single element, and so we don't have to really do anything with that, right? So that's why we kind of change or reorder the diagonals to be an increasing or decreasing based on what the problem statement says of where their position is, or if they are in the top right triangle or bottom left triangle of the matrix. So in example 2, we have our input grid to be 0, 1, 1, 2. Those are our 2 rows. And in this case, all we have to really do is, as you can see, there are 2 rows in the top left, 1 and 0, 2, and only 1 in the top right. All right, that's just 1. In this case, all we have to really do is just swap 2 and 0 to make sure that it does then become decreasing, because it is in the bottom left triangle of the matrix. In this case, it is the middle diagonal, right? And that's really it. And finally, in example 3, we have a singular element. It is just a 1 by 1 square or single cell input grid. In that case, we can't really do anything because it is just a simple diagonal of length 1 by itself. And we know that all diagonals that have exactly one element, or in other words, all corner diagonals or corner diagonals as well, they're already in order because there's just one element, and so we don't need to actually do anything. We just return the grid by itself, right? And that's kind of like a base case that we really don't need to directly address, but it is just kind of a base case to keep in mind. So for the constraints here, we see that the length and number of columns, or basically the number of rows and columns, are guaranteed to be n, where that value is between 1 and 10, rather small, kind of telling us that we can have a quadratic solution without getting a time limit exceeded because the input constraints are rather small. And every value in the grid is going to be between negative 10 and positive 10 to the 5th power. Right, which brings us to the main kind of observation and problem overview of how to actually solve this problem. And what is that main observation that we really need to make to kind of help organize this problem and help solve it in a more efficient and easy manner? Well, that is that each element actually belongs to a unique diagonal that we can actually identify by a difference formula, if you will. And that difference formula is I minus j. That's how we kind of identify where that specific unique diagonal is in the matrix as we iterate over the matrix, and we know that each element is going to belong to exactly one unique diagonal, right? Again, I minus j. What does I minus j really mean? Again, that is the group that is how we actually group matrix with the diagonal key. The I minus j is how we actually identify diagonals based off of their key, if you will. That's how we group matrix in those diagonals. And we have to actually sort each group or sort each diagonal based on its key by basically just seeing if it's in the bottom left or if it's in the top right. If it's in the bottom left, we have to sort it in descending order. And that's if the key is negative. If the key isn't negative, that means it's in the top right triangle of the matrix, and so we have to sort it in ascending order, right? And finally, we simply just reconstruct the matrix by popping from those sorted lists and returning our final answer of diagonals, right? So what are kind of the data structure that we really need to use? Of course, the main one is an answer array. That's going to be the resulting matrix that we have. Of course, it's going to have the same dimensions as the grid, but it's kind of like a separate matrix that we build off of for the different diagonals, right? And we also will have a diagonal hash map here, and that's how we actually use those keys to identify which diagonal we're in as we iterate through the input grid, right? It's going to be a map from key equals I minus j, and that's going to be basically a map from that key to a list of all the elements on that specific diagonal that we can get from the input grid as we actually iterate over it. So with that said, with that high level problem overview out of there, let's go ahead and start actually coding the solution. Now usually what I do for all matrix problems and square or rectangle Leetcode problems in general is I like to first get the number of rows and columns, or in other words, the dimensions of our input to help iterate over it in the future. Now in this case, we only have technically one dimension, and that is just n. Why? Because we have the same number of rows and columns. It is indeed guaranteed to be a square matrix like the problem statement and input constraints told us, and so all we have to do is just get the number of rows or columns, basically just length of grid, or even length of grid index 0, it doesn't really matter, and we just have to store that in our value n. That's just basically going to be the size of the grid, and that's going to help kind of iterate over our input and help guide our loops as we build our answer array as well, which brings us to the next line of code, which is actually building our answer array, or in other words, initializing it. So I'm going to call it answer. It is going to be a 2D array. Of course, it's going to have the same dimensions as our input grid. This is what we're actually going to return, except the only difference is, although it's going to have the same dimensions and same elements as our input grid, those elements may be in a different order for their corresponding diagonals to make sure that they're in descending or ascending order based on their key of where they are in the matrix. Now in this case, I'm going to initialize it first with just all zeros. It's going to be all zeros. It's going to have n rows, and it's going to also have n columns. And the way we can do that is just in Python, just have another separate loop here in the range of n. So basically we have n rows for all n columns, giving it an n by n or n squared area or n by n dimensions, right? Basically the same exact dimensions as, again, our input. Now, what we do from here is initialize that diagonal dictionary or hash map that I was talking about. I'm just going to call it diag to keep it short and to keep it easy to pronounce, and it's actually going to be a default dictionary. And in this case, the type of keys that we're going to store are going to be, of course, lists, because we need a list of all the elements in each diagonal, and we actually choose to go ahead and sort them in ascending or descending order. Basically, it's a default dictionary, which all that means in Python is even if we don't see a key in the hash map when we're actually trying to update it, it automatically sets it to a value of an empty list, right? And the way we know it's an automatic value or key value pair of an empty list, even if it isn't a key in the default dictionary, is that we're passing in the list parameter as our default data structure, right? It's basically auto-creating an empty list for any new key that we have in our matrix as we try to update them. And every key, again, is going to be how we actually identify our diagonals that we calculate from I minus j, and the list is going to actually store the corresponding grid values in each diagonal based on its key, as again, we iterate over our input grid. Now, once we've actually initialized this diagonal matrix, or rather this diagonal hash map here, now let's actually begin iterating over our grid and building our keys and diagonal hash map. So for every I and row in the enumerate of our grid, this is basically like the outer loop of our first nested loops here. We're basically going for every row, and for every row we're going to go in each column as well. So for every j and num in the enumerate of grid, or rather row, really all this does, what the enumerate does, is it keeps track of the value and the current index or cell value j as well for every corresponding row and column. So effectively, the outer loop is just going to loop over each row of the grid with its corresponding index I, and the inner loop here for every j and num is going to loop over every element in the row that we're specifically iterating over in the current iteration with every column index j and value num. Right, we're keeping track of all those values at once using that enumerate pattern, or that enumerate keyword, which is basically just a different way of iterating through an input. Now, for every cell value and for every, I comma j cell in the input matrix, let's actually compute its diagonal key. Basically, which diagonal it actually lies in, and how we actually identify that diagonal. And again, we identify that diagonal by doing I minus j. That was the whole point of that main observation here, right? We're computing the diagonal key as I minus j, right? That's going to be the same key that groups the same diagonal, right? Again, that's the main observation, going back to how we actually calculate that, right? I is, again, the actual current row or index that we're at, and j is going to be our column index. And so, kind of just a quick example here, if we were in the first loop here, I would first be 0 in the 0th row, and let's say j would be also 0 for this 1 here. And so the way we'd calculate this is going to be 0 minus 0, or in this case, the key would actually be 0, which would indicate that it is in the middle row. Again, what did we kind of discuss in the observation here? We knew that based on the key, we could actually identify which part of the triangle or which part of the matrix it was in. If a key was actually negative, it would be in the bottom left triangle, and if it was positive, it would be in the top right. Since 1 is in the middle row, we know that its key is going to be 0 minus 0, or 0, which is just neutral, if you will. It's neither negative or positive, and that's why it is in the middle row, which technically, for the sake of this problem, is still included in the bottom left triangle, as the problem statement tells us. That's the whole point of actually computing that I minus j value, to tell which diagonal it's actually in, and using that diagonal key to group it in the list of values in its corresponding diagonal, which we ultimately choose to sort in either ascending or descending order after we actually handle those cases, right? So once we've actually computed this key, now we'll actually to the diagonal, so diagonal at this key value pair, dot append the current value num. Right, effectively, now that we know that it is in this key, we're basically adding this current element number to the key, or basically to the diagonal, right? We're appending num into the list of values for its diagonal in the diagonal hash map, which again maps every key value identity for every diagonal with a list of all the values that are actually in the diagonal, right? That's the whole point of it. Now, that marks the end of our initial loop here, right? This is where we just simply all we do is build our diagonal hash map, and now we have to actually iterate over the diagonal itself to then choose how to actually sort our diagonals, right? In which diagonals to actually sort in which order, either descending or ascending. So now let's go ahead and handle that case. Let's exit this loop here, and let's start iterating over the diagonal itself. So for every key or key value identity for every diagonal in the diagonal hash map here, iterating through all the diagonal keys in our hash map, if the key is negative, again, what did that mean if the key was negative? If I minus j was negative, that means that it is in the bottom left triangle of the matrix. And so if that's the case, we have to sort it in non-increasing, or in other words, decreasing order, because we know that it is in the bottom left region as key is less than 0, meaning key is 0, or key is negative. And so the way we handle that is the diagonal at this key, which would just, again, correspond to the list of values in that corresponding diagonal, which we handled in the previous set of nested loops, we'd sort that. But by default, .sort in Python, the method in Python actually sorts it in ascending order. And since this is the case for the bottom left triangle of the matrix, we have to set reverse to be true. So as we're actually sorting this, we're going to sort it in reverse order to make sure that it is actually in descending order. So sorting that diagonals list of values in descending order. Else, if key isn't 0, we know that it's positive. That means, of course, it has to be in the top right region or the top right matrix. And so if that's the case, we have to then sort all the diagonals in this part of the region in ascending order. And so we just simply set diagonal for the corresponding key in this region and sort it regularly. We don't have to set reverse to be true because we're not trying to sort it in descending order, but rather in ascending order, right? That's the whole point of that check, if you will. Now, there's one last kind of quick case that we have to take care of, and this is actually to prepare to reconstruct the actual sorted matrix. For now, all we did was just grab our different diagonals and sort them in ascending or descending value, but we haven't actually built our answer array yet, because that's ultimately what we want to return, and that's what we have to actually do in the end. So once we actually get all the corresponding diagonals with their sorted values based on their region in the input matrix, then we have to actually reconstruct that sorted matrix back into our answer to be able to make sure that it's in the right format to return at the end. And so the way we do that is, again, another pair of nested loops here to actually build our answer for I in the range of n, again, the number of rows that we have, and for j in the range of n as well, the number of columns we have, basically iterating over each column j in every row. Basically, we're just going to build our answer, and we know we can compute answer at I at j to basically just be diagonal at its corresponding diagonal. And how do we get I comma j as diagonal? Well, it would just be I minus j. It'd be its diagonal key. And we'd actually pop from that diagonal and set that value to its corresponding cell, right? Basically, popping is going to actually give us the correct order there. We're popping the last element from the appropriate diagonal list of the current cell value I comma j and assigning it to its corresponding I comma j answer in the actual answer matrix. We're kind of reconstructing or constructing that answer matrix. And what popping actually does is it ensures that we're actually consuming from the sorted order correctly, right? To make sure that it has the right value for its corresponding index and its corresponding diagonal, whether it's descending or descending in the answer matrix, right? And finally, once we do that for every kind of cell I comma j in the answer matrix, we just return answer to be the fully sorted matrix of diagonals based on the regions in the initial input matrix, right? So unless I made in syntax 0, 0, this should be accepted and this should be a valid solution. And as you can see, this really is just about as efficient as you can get it to be. So again, on a high level, how are we really solving this problem? Effectively, we're just grouping each value of the matrix into buckets or diagonal keys based on its actual diagonal, which we compute by I minus j, and then sorting each diagonal appropriately based on where it is in the matrix. If its key is 0, meaning if it's in the bottom left part of the matrix, we're going to sort it in descending order, basically in reverse order, or just normal order or ascending order if it's in the top right part of the matrix. And finally, we simply just reconstruct that output matrix answer by actually popping values from the sorted lists or the sorted diagonals and preserving that diagonal position, but except with the sorted entries, right? And again, tying back to the main observation here, the grouping by diagonal technique basically just generalizes well to many matrix diagonal problems, not just this one in general, but anytime we want to actually handle one specific case, in this case sorting for diagonals based on their positions in input matrices. Now, that brings us to the final part of this video, which is the actual complexity part of this solution. And in this case, the runtime complexity quite intuitively is just big O of n squared. Why? Because, well, we really just have nested loops a few times here for every cell in our input matrix. So basically just n by n or n times n, which does give us n squared because we are traversing the entire matrix with nested loops here because we're sorting each diagonal where every cell is sorted exactly once across all the diagonals. And in the worst case scenario, all the diagonals are of course about length n, and there are 2 times n diagonals, and so the total sorting cost would be big O of technically n squared times log n in the worst case. But since n is really just less than or equal to 10, it is very, very small, and so really it's just big O of n squared for small n optimization and overall, right? So the sorting isn't going to really impact our runtime complexity too much because of how small our n value because of how small our n value actually is in our input matrix, and so we can kind of just disregard the big O of log n and just simplify it to big O of n squared from big O of n squared log n. And effectively for the memory or space complexity, also it is going to be big O of n squared. Why? Because we use this answer matrix which has literally the same dimensions as our input grid, n by n or n squared, and so it is also going to give us a big O of n squared memory or space complexity. So if you guys enjoyed the solution and learned something new, please consider liking this video and subscribing to my channel. And without further ado, I will see you guys in the next video. Bye-bye.